looked at how recommendation engines guess your preferences. Now we're moving into the structural efficiency that allows those systems to function at scale. Algorithm 46, hashing and Bloom filters. On our map of 50 essential algorithms, this sits in the cryptography and data category, specifically under Chapter 13, Algorithmic Strategies for Data Handling. Curious, it tackles a massive scaling problem. How do you check if a specific item exists within a set of billions of records without using the massive amounts of memory needed to actually store those records? This problem was solved by a counterintuitive trick from the 1970s. Today, it's a standard optimization for everything from Google Chrome's security layers to the high-speed data retrieval in Bitcoin wallets. In 1970, when this algorithm was first proposed, memory was a physical and financial bottleneck. Keeping a large lookup table resident in a computer's core memory was often impossible. Storage was built out of tiny rings of ferrite like these. Because every single bit was expensive and took up physical space, developers couldn't afford to store every key just for a simple membership test. Computer scientist Burton Howard Bloom realized that if a system could tolerate a small, controlled percentage of wrong answers, it could bypass these physical limits entirely. He proposed a filter that sacrifices absolute accuracy to achieve a massive reduction in space, trading a tiny bit of certainty for the ability to handle datasets that would otherwise crash the system. The Bloom filter follows a specific rule of asymmetry. It might occasionally tell you something is there when it isn't, but it will never tell you something is missing when it's actually there. This works because of how the filter is built. It's an array where bits only ever turn on, from 0 to 1, and they never, ever turn back off. Since a bit can't be erased, a 1 might be shared by multiple items, but a 0 stays a 0 until something specifically sets it. Because of that on-only rule, if the filter sees a 0 where it expects a 1, it gives you absolute certainty. That element is definitively not in the set. Adding cat passes through hash functions, flipping bits 1, 4, and 7 to 1. Dog flips 2, 9, and 11. Querying cat finds all ones, a probable presence. But querying fox hits a 0 at bit 3. That single 0 guarantees fox was never added. Since the only way to get a 1 is for an item to turn it on, a single 0 serves as an ironclad guarantee of absence. This approach is incredibly efficient. Its speed is what programmers call O of 1, meaning the search takes the exact same amount of time whether you're checking 10 items or 10 billion. And the memory needed, or O of M space, depends only on the size of the bit array, not the size of the items themselves. This chart shows the exact cost of that efficiency. To achieve a 1% false positive rate, you allocate about 9.6 bits of memory per element. To scale precision, increasing to 14.4 bits per element drops the chance of a false yes to just 0.1%. This logic is reflected in the Python code. The moment the query loop hits a single 0 bit, it triggers an early out, instantly rejecting the search without needing to check anything else. That instant rejection is the entire value proposition. It prevents a massive system from wasting valuable time and power on expensive searches for data that isn't even there. Google Chrome uses this to keep you safe. Instead of checking every single URL against a massive database of billions of malicious sites, it checks a local Bloom filter first. It only bothers to query the main servers if the filter gives it a maybe. Databases like Cassandra and RocksDB use the same trick to avoid unnecessary disk reads. By placing a filter in front of the storage, they skip checking files on a physical hard drive whenever the filter returns a definitive no. However, because false positives are inherent to the design, a Bloom filter can never be the final word. It's a preliminary check that must always be backed by an authoritative database for when it says yes. Bloom's 1970 method of embracing error has become a standard tool for reducing latency across global networks, allowing modern systems to handle traffic volumes that would otherwise be physically impossible. You can find more on the trade-offs of data handling in 50 Algorithms Every Programmer Should Know by Imran Ahmad. Next time, we're looking at Algorithm 47, Secure Hashing, or SHA, and how we create digital fingerprints that are designed to be impossible to fake.